Characterization of the effects of parameter uncertainty in Atlantis has been relatively limited. Some examples of what's been done is for here bounded scenarios. So for example, for acidification, looking at no acidification, low acidification to strong acidification. Another example has been looking at the effect of maximum parameters and minimum values for a specific parameter, and then see, in this case, how biomass behave between that maximum and minimum parameter. Another example, some work that we published earlier this year, is that we replaced the availability values that describe the food web matrix with standardized values. So instead of the actual ones, it was just like a range from 0.001 up. And when we just saw the effect of those standardized values. So why has parameter uncertainty been limited in how it's been characterized? So one reason has been that it's hard to run so many simulations and explore the space of parameters in Atlantis. Part of the reason is that when we run Atlantis locally, it's really easy, but the scalability and the consistency are low. So as we go from just our own laptops to multiple local computers, to servers, to cloud computing, to multiple virtual machines in the cloud and parallel computing, to high performance computing and batch processing, and then the use of Docker, we are going from really easy to use to harder to use, but we also go from low scalability and consistency to high scalability and consistency. So it's really in this space where we are in the cloud or we have high performance computing where we can really use that framework and explore this parameter space and the parameter uncertainty, and also aided by artificial intelligence and machine learning. So one way that I want to think about where to go with Atlantis simulations and with exploring parameter uncertainty is to think about these 5 aspects of simulations or a modeling framework. One is scalability, that we want to be limited by the ecological question that we're asking and not by the technical specifications on how many scenario runs we do or what those scenario runs are. So we're able to explore the whole parameter space as needed. We want to be able to reproduce our errors and our results. We want those to be extendable and consistent. We want to be able to apply what we learned to other models and to other research problems. We want transparency in that the installation and the run processes are clear, regardless of the operating system, and that's something that Docker helps us with. And then we also want ease of use. We want to be able to reduce troubleshooting and the need for support. So one way that in our group we moved towards these 5 things is by using cloud computing and obviously GitHub. So we've used Azure, which is the Microsoft's solution for cloud computing. And that's been thank you to the support of the AI for Earth program in the last few years. So what I'm going to talk to you about is how we use machine learning to assess how uncertainty in dye composition influence the assessment of oil spill impacts, as an example of how we can use AI to explore parameter space. So this is research that has already been published, and we use the Gulf of Mexico model that was developed by Cam Ainsworth. And this is just a general diagram of their model. So we know that uncertainty in the availability matrix may influence scenario results. So in this case, when I mean the availability matrix, I'm talking both about the presence of the linkages between functional groups that describe that feeding relationship, but also the strength of those linkages. So in this case, we know that those values come from we drew those values from a statistical distribution, and depending on where on that statistical distribution you're taking them, then we know that there's going to be a change in the response in the model, or what, and eventually on the scenarios that we run. The Gulf of Mexico model was developed specifically to model the effects of the Deepwater Horizon oil spill, which occurred in 2010. And we know oil spill disrupts ecosystem services, and in the case of the Deepwater Horizon, it decreased fish landings, it had sublethal effects, and there are indirect food web effects. And this is just to show you how big the the oil spill was in the Gulf of Mexico. The blue is the model extent of how far those oil spill products extended. The brown is how what was actually observed from space using remote sensing. That was like the oil footprint. The yellow is some other modeled results that were not seen by satellites, but were expected to be there. And then I just want to draw your attention to this dashed line, which was the area that was close to fisheries. So you can see it was a pretty large extent. So the food web matrix in the Gulf of Mexico model was based on gut content analysis. So in addition to existing data, there was a pretty extensive effort to get samples and then look at the stomachs. And then that data was used in a statistical method that combined these multiple data sources while accounting for uncertainty. So this shows that process, and here's the reference, but there are several references describing and the updates to this method. So it's the statistical fitting of diet composition, where the aggregate fish diets are bootstrapped, and then we quantified the diet estimates and the associated error using a maximum likelihood approach. So we had these marginal beta probability distributions. So we're the estimates that the likely diet contribution of a given prey to the diet of the predator. So we took what the most likelihood value was out of these distributions. So what we did to quantify uncertainty in these distributions is first we bootstrapped the data, as I just showed. So we had these beta distributions, and we just set up the analysis so that the error ranges have 10,000 values. So each of these distributions has 10,000 values. Then we sampled the distribution using an approach called the Latin hypercube. So we had 1,000 samples. So this is just an example of how that method works, so that you sample the whole parameter space. So we had the, as I described, the availability matrix, but instead of just having one, we had 1,000 alternate availability matrices based on that sampling. So as a result, we had 1,000 simulations. And what made this being able to do 1,000 simulations was cloud computing and parallel computing. And each of those simulations had a scenario that simulated the oil spill from the deep water horizon. So once we had those 1,000 simulations, what we wanted to do is say, well, now we want to explore the full parameter space. We don't want to just do a sample. We want to do the 10,000 simulations. So we sampled the 10,000 availability matrices. Sorry, the 10,000 values from the matrices. But one thing is to do 1,000 Atlantis simulations, but 10,000, it starts getting prohibitive. So what we did is we developed a statistical emulator or meta model, which is a model that describes the relationship between, in this case, these availability values from the simulations and the biomass and catch. So we use that relationship, and we use both regression methods and machine learning methods to describe that relationship, and then use those models to then, or emulators, to then run the full parameter space, those 10,000 emulations. So we used two different categories: the regression methods, which were the generalized linear model and a multivariate adaptive regression splines, and then these machine learning methods, which were a combination of tree-based methods and a neural network approach. So once we created those emulators, then we used them to do 10,000 Atlantis emulations. And these emulators are much faster representations of Atlantis. So they don't take as much time. They don't need a single processor as Atlantis would do. So it's a quick way to explore the parameter space. So this diagram is called a Taylor diagram, and it shows us the emulator performance. So in general, the random forest and the extreme learning machine models, which was the neural network approach, are the ones that deviated most from the observations. But looking at these three aspects, the standard deviation, the correlation with observed data, and the center of root mean square, these emulators had pretty good performance. So these results I'm going to show you are the simulated in blue and in yellow the emulated trajectories for the biomass and catch of fish gills. And the shaded areas show the range of outcomes observed in the uncertainty analysis. So the top are the simulations, so there's 1,000 of them, and the bottom are the emulations using the meta models. And these are, again, grouped into fish gills. So there's multiple functional groups in each diagram. And you can see when you just look at them, you're like, well, they kind of look very spiky, especially the emulators. So I'm also going to show you some of the individual model results, which are a little easier to interpret. So these are the simulated and emulated biomass trajectories. And I've highlighted some specific groups here, so we can compare. And this is similar to what happened with most of the functional groups in the model. So we have groups, for example, here pinfish, or maybe here gag, where the simulated and the emulated results actually match up really well. And then we have cases where the emulator and the simulator are kind of follow the same trajectory but are different, but we would expect that, right? Because here in the emulator, we're exploring a larger space. And then we have places where here, like the pinfish, where we have these really spiky results where we go in ranges that are not present in the simulations. So one likely explanation for this is that there are cases where if you had these trajectories or certain behavior in the simulation, the model would likely crash or the species would go extinct. And that might not happen in the emulation. But it was interesting to see, for example, here's another case where those simulations and the emulations track pretty well. So what was the overall conclusion, or what's the implication of this analysis of parameter space? So one thing we wanted to look at is recovery. So how does the ecosystem recover, and how does the choice of where you land in that distribution and those availability values, how it's going to affect that recovery? So this diagram shows the biomass minima versus years to recovery. The points are simulated and emulated results, so like these colored ranges, and the solid black triangles are the base model. So we can see there's quite a bit variation between how many months it takes to recover, so what the implication is of how we conclude the results from the model, and the availability value that we used. So in conclusion, we found that uncertainty in diet compositions had a large effect on ecosystem model outputs. So that could influence how we're applying, what the conclusion of the results of the model are. In this case, what the damage assessment of oil exposure was on commercial target species. But we did find that emulators based on machine learning can aid in model parameterization. But more research is needed on what the sample size required is. So even doing those 1,000 Atlantis simulations was extensive work, and it required extensive computing capacity. So if we could know that developing an Atlantis emulator does not require 1,000 simulations, maybe it just requires 100 or 200 or 300. Just knowing that and how to develop those relationships would be really useful, and it's for sure something to research on. Thank you.